You know that feeling when you're starting to code something new and you type in print, "Hello world."
Oh, yeah, absolutely.
You
That
know,
first little check.
it's that first step, right? Just making sure everything's working. You've got the basics
Oh,
down.
exactly. Well, there's kind of a similar thing in quantum computing, a hello world, if you will.
And that's what we're diving into today using Qiskit, specifically Qiskit 1.x.
That's the plan. We're going to unpack the sort of fundamental workflow, drawing from a really good Qiskit YouTube video.
Ah, the Coding with Qiskit 1.x series, episode 3, I think, with Derek Wong.
That's the one, hello world. It's a great source for understanding how you actually start programming these quantum computers. Think of this as, your shortcut to getting up to speed.
Okay, so our mission for this deep dive, break down the essential steps. We'll start with a simple example.
A 2-qubit Bell state
Yep, a classic. And then we'll see how those same ideas scale up, like way up.
to a 100-qubit GHZ state. Wow. So we're not just looking at code, we want the concepts behind it. Precisely. And Qiskit actually gives us a nice structure for this. They're patterns for quantum workflows.
Right, I remember reading about those. There are 4 steps.
4 main stages, yeah. First, you map your problem onto quantum circuits and operators. Figure out how to ask the quantum computer the question.
Okay, map the problem, step 1.
Step 2 is optimizing that circuit, making it runnable, efficient, especially for real hardware.
Makes sense? Then step 3.
Execution, running it, either on a simulator or, the actual quantum hardware.
And finally, step 4, getting the answers back.
Post-processing, exactly, analyzing the results. So we'll follow these 4 steps for both the 2-qubit and the 100-qubit cases.
Perfect. Let's start with step 1 then, mapping the problem for that 2-qubit Bell state. What is a Bell state exactly?
Ah, good question. It's a really fundamental state in quantum mechanics. It involves 2 qubits, and they become entangled.
Entangled, meaning linked together in some weird quantum way.
That's a good way to put it. They're in a superposition, sort of 0 and 1 at the same time, but linked. It's specifically the state where they're either both 0 or both 1, written like 0, 0 plus 11.
Okay, 0, 0 plus 11. How do we actually make that happen in Qiskit?
So the video shows this clearly. You start with Qiskit's quantum circuit object. Pretty standard.
You tell it you want 2 qubits.
Right, quantum circuit 2. Then the magic happens with 2 quantum gates. First, a Hadamard gate.
The H gate.
Yep, the H gate. You apply that to the first qubit, which is qubit 0 in programming terms.
And that puts it into superposition, like that quantum coin flip idea.
Exactly. It's now kind of 0 and 1 simultaneously. Then comes the second gate, a CNOT gate.
CNOT, or CX, that one needs 2 qubits.
It does, a control and a target. If the control qubit is 1, it flips the target qubit.
Okay.
And because our first qubit is in that superposition state from the Hadamard gate, this CNOT gate creates the entanglement. It links them.
So the H gate creates the maybe, and the CNOT creates the linked maybe.
Hey, yeah, something like that. It results in that Bell state, 0, 0 plus 11, where their outcomes are correlated. It's a purely quantum thing, this entanglement. No classical equivalent.
And the video showed you can actually draw the circuit. See the H and the CNOT.
Yeah, circuit.draw. It's super helpful for visualizing what your code is actually building. You see the H on qubit 0, then the line connecting 0 and 1 for the CNOT.
Okay, so we've built the circuit. But step 1 is mapping to circuits and operators. How do we check we actually made a Bell state?
Right, good point. We need to measure things. And in quantum, we talk about measuring operators and finding their expectation values.
Expectation values. Like the average result, if you ran it tons of times.
Basically, yeah. For a Bell state, theory tells us certain 2-qubit operators, specifically ZZ and XX, should have non-zero expectation values. That's a big sign of entanglement.
ZZ and XX, meaning applying a Z-gate measurement to both, or an X-gate measurement to both.
Kind of. It's measuring the correlation in the Z basis and the X basis. But then single qubit operators like ZI or IX.
Where I is just identity, like doing nothing.
Exactly. ZI means Z on the first qubit, identity on the second, IX is the other way around. Those, along with XI, should have expectation values really close to 0 for a proper Bell state.
So these operators are like our measurement tools, our probes. How do we define them in Qiskit?
Qiskit has a class for this, polisump. You import it from qiskit.quantuminfo.
Polish them up. Got it.
And then you can create them pretty easily just using strings, like literally the strings ZZ for the ZZ operator.
Oh, nice. So ZIXXXXXI.
Yep, just like that. The video shows creating these and sticking them in a list, ready for later.
Okay, step 1 complete. Map the Bell state problem to a circuit and the ZZ, XX, ZI, XI, IX operators.
Yeah.
Now, step 2, optimization.
Right. Now, optimization or transpilation is usually super important for real hardware, dealing with qubit connectivity, which gates are native.
Translating our ideal circuit to what the machine can actually run.
Exactly. But
Figure it out.
for this first example, the video uses the local air simulator.
Ah, the software simulator running on your own computer.
Right. And because it's a simulator, it's flexible. It can handle this simple 2-qubit circuit directly. So for this specific case, we actually skip step 2. No optimization needed.
Convenient. So straight to step 3, execution. Running the circuit on this air simulator. How's that done?
This involves using something called an estimator primitive. It's designed specifically for, well, estimating those expectation values we talked about.
Okay, an estimator. Where does that come from?
From Qiskit.primitives. And the video actually shows a common little hiccup here.
Oh, what happened?
A module not founder. The Qiskit package wasn't installed yet in that environment.
Ah, the classic forgot to pip install moment. Happens to everyone.
Totally. So Derek, the presenter, shows the fix, activate the environment, pip install Qiskit. Simple enough.
But then there's that crucial extra step.
Restarting the kernel. Yes, if you're in a Jupyter notebook or similar, you have to restart it after installing so it actually sees the new package.
Good reminder. Okay, so Qiskit is installed, kernel restarted, now we can use the estimator.
Yep. You create an instance of it. Then you call its run function.
And what do you pass into run?
The quantum circuit we made and that list of operators, ZZ, ZI, etc.
Okay,
Yeah.
circuit operators. Makes sense.
There's a small note in the video about this specific version of the estimator, though. It needed the same number of circuits as observables.
Oh, really? So if you have 5 operators, you need to pass the circuit in 5 times?
Kind of, yeah, or structure it that way. It's a bit awkward. They mentioned the newer V2 primitives are much smoother in that regard.
Good to know. But they make it work here. And since it's a local simulator, the results are fast.
Instantaneous, pretty much. No waiting in a queue for hardware access. You get the job object back right away with the results.
Nice. Okay, execution done. That leaves step 4,
Mm-hmm.
post-processing and plotting. What do the results look like?
Well, the estimator actually does a lot of the heavy lifting in terms of calculating expectation values. So the post-processing is mainly about visualization.
Making a graph.
Exactly. Using matplotlib.pyplot, the standard Python plotting library, they set up labels for the x-axis corresponding to our operators, ZZ, ZI, XXZI, IX.
And the y-axis is the expectation values from the results.
Precisely. They extract those values from the job results. Then they just plot points, operator name on the x, expectation value on the y.
Yeah. Does it look like a Bell state?
It does. The plot clearly shows the expectation values for ZZ and XX are really close to 1.
Which is the sign of entanglement we wanted.
Right. And conversely, the values for ZI and XI and IX are all very close to 0, just like the theory predicts.
Perfect. Any small errors?
Tiny deviations, yeah. The video mentions this is likely due to simulated shot noise, the statistical noise you'd get from a finite number of runs, even on a perfect device. It mimics reality.
Okay, so a successful hello world. We made a Bell state, measured it, confirmed it. Qiskit works.
Exactly. But then the video takes a big leap.
To the 100-qubit GHZ state, scaling up dramatically.
Right. And the cool thing is seeing how that same 4-step workflow still applies, just with more complexity.
So what is a GHZ state? Greenberger-Horn-Zeilinger.
That's the one. Think of it as the big sibling of the Bell state. Bell was 0, 0 plus 11. An n-qubit GHZ state is 0.0 plus 11.1.
So all zeros are all ones across all n-qubits.
Yeah.
Entangled across the whole system.
Exactly. Maximum entanglement across many qubits. The video really stresses that the Qiskit patterns hold up even at this scale.
Okay, let's follow the pattern. Step 1, mapping the problem for 100 qubits. The circuit must be bigger.
Considerably. So to make this manageable, they write a Python function. Get Q4 in qubits En.
Ah, a reusable function that takes the number of qubits, n, as input. Smart.
Yep. Inside, it creates a quantum circuit N. Then, similar to the Bell state, it starts with a Hadamard on qubit 0.
Putting the first qubit into superposition.
Right. But then to entangle all the others, it uses a chain or ladder of CNOT gates.
Ladder, how does that work?
It applies a CNOT from qubit 0 to qubit 1, then a CNOT from qubit 1 to qubit 2, then 2 to 3, and so on.
All the way down the line, linking each one to the next.
Exactly. CNOT from I to I plus 1, all the way up to N2 and N1. This propagates the entanglement across the whole set.
That makes sense visually, like a domino effect of entanglement.
Kind of, yeah. The video shows the drawing for N10. Just to visualize it, you see the H and then this cascade of CNOTs. It looks pretty neat.
And then they just said N100 to get the actual circuit.
Yep. Generates the 100-qubit GHZ circuit object. It's big, but the principle is the same.
Okay, circuit done. What about the operators for this 100-qubit case? Still ZZ and things.
The goal shifts a bit here. With 100 qubits on real hardware, noise becomes a major factor. So they want to probe how correlations hold up over distance.
Ah, so measuring entanglement between qubits that are far apart on the chip versus close together.
Exactly. The idea is noise might kill the correlation more easily over longer distances.
Just what operators do they use to test that?
They create operators that are ZZ-like but spaced out, so always a Z on qubit 0.
Okay, Z on the first one.
And then another Z on qubit N, where N goes from 1 all the way up to 99.
So Z on 0 and Z on 1, then Z on 0 and Z on 2, Z on 0 and Z on 3.
Exactly. And crucially, identity operators on all the qubits in between.
So like Z on the NEI, then Z on ZIAD, then ZI.ZII, and so on.
Perfect. That's exactly it. You get 99 of these operators measuring correlations at distances 1 through 99.
That's clever. But representing those must be tough. 100 qubits, mostly identities.
Right, so they don't use Paul Sum up here. They use sparse polyup from Qiskit Info.
Sparse, because most of it is identity.
Precisely. It's way more memory efficient for these large sparse operators. The video shows generating the strings programmatically and then creating these sparse poly objects.
Okay, mapping done for 100 qubits, circuit generated, sparse operators defined. Now, step 2. Optimization. This must be critical now.
Absolutely essential. You cannot just run that 100-qubit ideal circuit on real hardware. It won't work.
Why not?
Real chips have limits. Qubits are only connected to certain neighbors. They can only perform specific native gates. You need to transpile.
That translation process again, adapting the circuit.
Yes. It might involve swapping qubit assignments, breaking down gates into native ones, maybe merging gates. It's complex. The video notes that this is where a lot of quantum computing expertise lies, effective transpilation.
So how do they approach it for this 100-qubit example?
They decide to target a real IBM quantum backend. They import Qiskit runtime service to connect to the cloud platform.
Which machine did they pick?
In Brisbane, it's a 127-qubit device. So plenty of room for our 100-qubit circuit.
Okay, they have the target. How do they optimize for Brisbane?
They use a tool called Generate a Preset Pass Manager. You feed it the back-end information.
Like Brisbane's connectivity map and native gates.
Exactly.
Yeah.
And it spits out an optimization pipeline tailored for that specific hardware. They set optimization level 1, which is a sort of basic level of optimization.
Why only level 1?
Probably to keep the classical computation time down for the demo. Higher levels can take much longer to run.
Makes sense. So they run this pass manager on the 100-qubit circuit.
Yep, using its run method, which effectively transpiles the circuit. And crucially,
Let me guess. You have to transpile the operators too.
you got it. The circuit transpilation might have remapped logical qubit 0 to physical qubit, say, 53. The operators need to reflect that new layout.
How do they do that?
They use the layout information stored in the transpiled circuit object. There's a method like apply permutation that adjusts the operators accordingly.
Okay, circuit and operators are now transpiled for in Brisbane. Step 3, execution on the real deal. How's that different?
It uses a different primitive, estimator v2, from the Qiskit runtime package. This one's designed for running jobs on the IBM cloud backends.
Estimator v2, is it easier to use?
The video suggests it is, yeah. More intuitive for submitting jobs and getting results back from the cloud. They also import options to configure the run.
Options. Like what?
This is where you control how the job runs on the hardware. They set resilience level 1.
Resilience for error mitigation.
Yes, level 1 usually means basic measurement error mitigation, correcting for errors when reading out the final zeros and ones.
Okay, what else?
They set optimization level 0 inside these runtime options.
0. But didn't we just optimize?
Exactly. We already did the transpilation in step 2, so we tell the runtime not to try and optimize it again.
Got it. Anything else?
Yes, something interesting. Dynamical decoupling, true. And they specify a sequence type.
By 4.
Dynamical decoupling. What's
It's a
that?
technique to combat errors while the qubits are just sitting there, idle, during the computation. It involves applying carefully timed pulses.
Like actively protecting the qubits from noise?
Sort of, yeah. The by 4 sequence is one specific pattern of pulses known to work well for certain types of noise on superconducting qubits like IBM's.
Fascinating. Okay, so they've set up the estimator V2 with the Brisbane backend and all these options. How do they launch the job?
Just estimator.run, passing in the transpiled circuit and the transpiled operators.
And that sends it off to the cloud.
Yep. It returns a job object, and they print the job ID. That ID is your key to tracking it on the IBM Quantum website.
These jobs can take time to run, right? Waiting in the queue? They definitely can. So for the sake of the video, they don't wait. They actually pull up the results from a previous job they ran with the exact same settings.
Ah, smart. Like on a cooking show where they have one already prepared.
Exactly. They show how to use service.job with the old job ID to retrieve the completed results instantly.
Okay, practical solution. So we have the results from running the 100-qubit GHZ state on in Brisbane. Step 4, post-processing. What do we see?
The main goal now is to visualize that distance correlation relationship we talked about.
So plotting the expectation value of those Z0s, Z operators versus the distance and...
Right. The x-axis is the distance from 1 to 99. The y-axis is the expectation value.
Okay.
But to make the trend clearer, they do one extra step. Normalization.
Normalization, how?
They take all the expectation values and divide them by the value they got for the closest pair, 0 and Z1, distance 1.
Ah, so you see how the correlation decays relative to the strongest nearest neighbor correlation.
Oh, precisely. It sets the baseline correlation at 1 for distance 1, and then you see how it drops off.
Clever. And what does the plot show?
It shows a clear decay. The normalized expectation value drops noticeably as the distance between the Z operators increases.
So the entanglement or correlation is weaker between qubits that are farther apart on the chip?
That's what the data suggests, yes. It's a direct visualization of noise and decoherence impacting the quantum state over larger scales in the processor.
Which is expected on current hardware, right?
Absolutely. It's the reality of NASQ, noisy intermediate scale quantum computing. The video does mention, though, that better transpilation, higher resilience levels, more advanced mitigation
Could improve this. Give you less decay.
Potentially, yes. Those estimator options give you levers to pull to try and fight the noise. It hints that these results aren't the absolute best possible, just what you get with the specific setup.
It really shows the challenge, doesn't it? Even for this GHZ state, which uses relatively simple gates. Noise is a big factor at 100 qubits.
It really does. It highlights just how hard it is to maintain delicate quantum states as you scale up.
So we've journeyed from the hello world 2-qubit Bell state on a simulator all the way to a 100-qubit GHZ state on real hardware.
And we followed that same 4-step Qiskit pattern the whole way. Map, optimize, execute, post-process.
It really drives home that these fundamental patterns and tools are scalable. The complexity increases, sure, but the core approach holds. That's the key takeaway for you listening, I think.
Absolutely. You start with these building blocks, and you can tackle progressively harder quantum problems using the same framework. Qiskit provides that structure.
And that observation about the noise decay, even in the 100-qubit GHZ run, it's quite provocative, isn't it?
It is. It makes you think about the path forward. How much better can we get with error mitigation on current hardware? And what will it take to get to truly fault-tolerant machines? It's the central challenge.
Definitely food for thought. Where should people go if they want to dig deeper into this? Transpilation, error mitigation.
Oh, the Qiskit documentation is fantastic. And the IBM Quantum Experience website has tutorials, explanations of the backends, details on the estimator options.
Lots to explore. You could try different optimization levels, different resilience settings, maybe even different dynamical decoupling sequences we mentioned.
For sure. Plenty to experiment with if your curiosity is piqued.
Well, this has been a fascinating journey through the quantum hello world and beyond. Thanks for guiding us through it.
My pleasure. It's exciting stuff. Keep exploring, keep thinking quantum.